I'm still happy the previous owner planted so many and they're blooming. Okay, where is homework one? Right here. Okay, so it talks about a 1D wire, and you remember we drew the subbands. And so, does anyone have any thoughts on how one might determine how many subbands are filled? So let's see, the energy is going to look like this. So before we before we go to 1D, for a 3D, we basically have these eigenvalues, right, labeled by K. And K was a combination of Kx, Ky, Kz. So go back to that calculation and see how we determined EF for a given density. Right? Just review that and try to see if now your dispersion looks more like these subbands and another index here, Kz. So now your energy looks like Kz, N, and M. This is density here. And then again, you want to do the same problem. Given a certain density, how would you fill them up? So try to think in terms of counting and then see if you can convert one of them into an integral and try that. And so give it a shot, and then if you still have questions, we can discuss it maybe tomorrow. Okay. Any other questions about this? Yeah? Okay. Start working on it because, if you have questions, we'll discuss it. Every class we can spend a little bit of time as you raise questions, so that coming up to the submission date, everybody will have it. And the idea of this is keeping in mind that data we looked at for a carbon nanotube. And I'm trying to do it now with gold or whatever this material is. Yeah, it's a gold nanowire. Okay, so for today's discussion, I want to review a few things from the last class and then talk about, let's see, let me try to put up that question. Okay. Capacitance. So, we've been talking about nanodots, and we are trying to tunnel into nanodots. So I thought we should have some idea about numbers. What are the energy scales we are looking at? So let's see, did people try to work out what is the capacitance of a 5 nanometer dot? Anyone tried? Everyone tried? Okay, good, because at some level we are talking about a capacitance, and what is the formula we have for that?
4 pi epsilon r.
Yeah, 4 pi epsilon r. Jason, did you pick some values for this?
Yep. Let's see, I got about 3 times 10 to the minus 18.
Oh, what did you pick for epsilon?
Let's see, 12 times the vacuum pressure. So I just
so 4 pi epsilon naught, and then some ER,
yep,
which is a number for that particular material. So these symbols are the same, times R. And this is some, you have to look up Wikipedia for that.
Right.
And it was funny because if I tried, I could not remember what this is called. So I tried epsilon sub 0. And then it takes you to somebody's paper, who's typed in epsilon sub 0. But then I kind of remembered, how did you guys find it? You went to a book? Or Wiki? Wiki. What did you type in to get that?
It's just on the page for capacitance.
Oh, nice.
What did you say?
I looked up the capacitance of the sphere,
Yeah.
and it's got the formula, and it also has the values.
It had the value? Because I looked up capacitance, I couldn't find the value of that. Anyway, it's called permittivity of free space, and this is the first time after years of teaching E&M, I found out why it is called that. It's like how much electric field is permitted through, in this case, vacuum or material. That's the basis of permittivity. I never paid attention. Okay, so it has some value which you can look it up. What is the value?
8.8 times 10 to the 12.
10 to the?
Negative 12 farads per meter.
Yeah, so this is the important thing, farads per meter. And that's already going to tell you your unit is going to be tiny. ER depends on the material, and so ER is approximately 10 for semiconductors. It's about 1 for a metallic system. And, and R, you put down 5 nanometers. And that itself, nano is 10 to the minus 9, it will add to that. So C comes out to be about, you said 3, let me just write 1 attofarad. Atto is our, yeah, question?
You said for a metallic system it's about 1. For vacuum it's about 1.
Yeah.
For a metallic system it's huge, right? Like those two things.
So again, it depends on where we are looking at this quantity. So it becomes, epsilon becomes a function of omega. And so that we will maybe talk about this in the next one when I discuss nanometallic particles. But the quantity I'm talking about, so it has some behavior as a function of omega, which, it will go through all these peaks, things like that, something like this. And this number is the value at 0 frequency. Then, if it has some particular bound states and it causes some resonances, you will see these kinds of peaks and so on. And then, you can get what is called a plasma frequency, and then it has some behavior like that at high frequency. But kind of we're talking about this 0 frequency dielectric constant. So a metal screens perfectly, and that's why that number is very close to 1. In an insulator, you can develop some polarization. So this is reflecting the polarizability of the material. And in a metal, it just screens perfectly. So and so this is the new unit, attofarad. Atto, which is defined to be 10 to the minus 18. So we have already gone from the one before that, 3 orders bigger is peta. So we talked about lasers being petawatt, that's plus 15. This is now negative 15, would be also called little petafarad, and then, no, femtofarad, and now this is atom. And so the size of the nucleus is a femto, meters, and this is farad. Okay, very good. Now, what is the charging energy that you got? Did you try it, Ishan? The charging energy? So this would be E squared over C, and you got 0.3 electron, 0.3? Is that what others got? What did you get?
0.01.
If you set epsilon r equal to 1, you get 0.3.
Ah. So we want to put in again, you have to, did you put epsilon r equal to 1? Okay. So E square over 4 pi epsilon naught epsilon r times r. And again, you shouldn't, you don't have to evaluate everything. You know this. It's useful to recall the hydrogen atom all the time. And so Howard, that's also for your exam. If you start plugging in 8.85, it's like, so you have to remember the hydrogen atom. E squared over 4 pi epsilon naught over 2a naught. So usually we don't even bother to write this. We just say E squared over 2a naught because in CGS units that doesn't appear. And this is just 1 Rydberg times we have 2a naught over r and then 1 over epsilon r. So this we already know is 13.6 eV, right, which is 10 in my kind of units. And so this is about 10, and from here we get a factor of A naught is half an angstrom. So that's 0.05 nanometers. And our R is 5 nanometers. So that itself is 10 to the minus 2, and then we get another 10 to the minus 1. So that's 10 to the minus 2 eV. So that is 0.1 MeV. Yeah.
No.
No, it's
10
point-
MeV.
point-
10.
That's 10 MeV. Is that what people know? Yeah,
Mhm.
10 MeV, good. And that, in terms of temperatures, is equivalent to 100 Kelvin. No, am I doing that right? I'm going wrong today. So let's see, 10 to the 4 Kelvin is 1 EV, or 10 Kelvin is 1 MeV. That's another thing to remember. How about again for your exam? 1 MeV, so that's, it is 100, yes, I did write that down. It just sounded high because these experiments are done at millikelvin temperatures. Some of them. So it depends on the size of the dot. I picked a very tiny dot. So if they are bigger, then your charging energy will be smaller, and then you have to go to lower temperatures.
You want the charging energy to be high though, right? So that thermal activation is.
Yeah, you want the charging energy to be higher than the temperature. So our charging, so this is equivalent to this temperature. So here I should write equivalent to that temperature. And that means that the temperatures you work with, so charging energy is 10 milli-electron volts, which is equivalent to 100 Kelvin. This implies that we want EC to be greater than KT to observe charging effects. And that implies that experimental temperatures are on the order of, let's say, 10 Kelvin, or 1 to 10 Kelvin. You want to be much lower. Okay, so these are the kinds of estimates one can make. So, and then the other thing was, okay, that's a no-brainer. How much voltage change would happen? Yeah, just the volts. You remove the E. Okay, so everybody's happy with that? These are the scales we are talking about. And today I'm going to re-emphasize some of these things in the data. So let's see. I want to show you a few things which I've put up on the web, and I've put up all the lectures now on the web. It took me a while to write them, but so I finally came up with a nice way a minimal way to depict the tunneling into a quantum dot. Okay, this is also going to be called a single electron transistor, as I will show you by the end. Why this is called a transistor and so on will come out. But remember this configuration. This is the configuration for what is called a single electron transistor. And what it has is something we discussed already. There's a source, there's a drain, you're biasing it with a voltage, and then there is a gate voltage, which is capacitively coupled with some capacitance Cg, which is different from the capacitance of the drain. And that is just being used to push the levels up and down. Any questions about this? Is everybody clear about what is going on in this dot? This is of fundamental importance. It will come up again and again, so I want to be sure everyone understands this. We are talking about a tiny dot, 5 nanometers to a few hundred nanometers, and then we are tunneling into this from these leads. The electron comes in this lead and hops onto the dot and hops back on again and goes around the circuit. This one, it's just being used to move the levels. Okay, so there are all these attofarads, so on and so forth. Okay, so we discussed things like we want to have energies which are greater than kT, and also tunneling times which are very long, so that the electron is not just tunneling back and forth but sitting on the dot, and that will allow us to see Coulomb blockade. So the things that we want to, the four effects are these: Coulomb blockade, Coulomb oscillations, Coulomb staircase, and Coulomb diamond. Okay, so these are the four issues, four concepts or four phenomena that come up because of this quantum dot. And I just thought I will review all of those four. So, and I didn't quite do it this way last time, but I found this is a useful way to think about it. So the energy of the quantum dot basically is the total charge on the dot, q square over 2c. 2 is just coming in because if you remember the energy of the dot, we kind of say E square over c, but there's a half CV square. If you go back to it's like your kinetic energy is half mv squared because you do an integration and that brings in that half. So you get half CV squared, and V is basically, C is by definition Q over V. So you get half and then this gate is also interacting. The gate also has some charge, and that is interacting with the electrons in the dot, and you have the second term. And I can combine those and get, I can square it and remove this factor and write this energy in this way. So it's Ne minus VGCG, which is the total charge coming from the gate. So the gate is basically just moving these levels squared minus something, which does not depend on the number of electrons. So what we want to look at is the energy for n plus 1 or n minus 1 relative to En. And what that gives you is a set of these parabolas. And this is useful to think about the charging effects in this way. So if you look at these parabolas, it basically shows the energy as a function of the gate voltage. And what you see is that, let's say when Ne is equal to 0, you get a parabola here. When Ne is 1, so n is 1, it is shifted and you get the second parabola. And then a third one for n equal to 2. So for each particle on the dot, you get these parabolas, and there are points in between where the two parabolas intersect. And those are the points where where there's an uncertainty, or where the energy for 0 and 1 are identical. Here, between 1 and 2 are identical. So these are the voltages at which you will have current flow. Because now the energy for both configurations is the same.
What was the x-axis there? The gate
Oh, sorry,
voltage? Or
you should just think of it as the gate voltage.
Okay. Scale by.
Cg is constant. It's the capacitance of that junction between the gate and the small particle, but it's basically a constant. So now, if you're sitting at a particular gate voltage, so if I look at that vertical arrow, so for a fixed value of Q0, or you can think of the gate voltage, there is a minimum cost to change the number of electrons on the dot. Right? So basically what this is saying is, I would have to, so this is bringing the role of the source drain voltage. So here, if I want to change the number of electrons on the dot, I would have to supply a finite energy. Whereas here, it can just change spontaneously, just by tunneling. So this difference is what is achieved by applying the source drain difference. Okay. I'm just throwing this in as yet another way of thinking about the whole story. Okay, now we come to all those different phenomena that I mentioned, and so again, let me draw my here, as we were discussing, what is done in the beginning, think of, at this point, I haven't written this, I should have done that. What is done is to apply a very negative voltage. Okay, when you apply a negative voltage, it pushes these electron levels way up. So let's do that. So here's the dot, and this is the chemical potential. And it has pushed the level way up. So somewhere here. Okay, this is with a very negative voltage on the gate. This is my gate. So if the voltage is extremely negative, the levels have gone way up and nothing is tunneling. Then as the level is pushed down, you can start to form a pathway for tunneling. But if the two chemical potentials are identical, you're not going to get any current because the two, you have equal amounts. There's no potential difference between the source and the drain. So you have to now tilt it, make a potential difference to start getting some current. So that is the origin of that diamond, because you are playing around with two variables. One variable is the gate voltage, and the other variable, so just as a function of gate voltage, for some fixed, here I should have written fixed source drain potential. So for a fixed source drain potential, this will not, the picture I've shown you is not going to really happen at exactly zero bias. But if I tilt it, then I will start to get current. Is that right? I think that is right. Because otherwise, the two levels are exactly at the same voltage, at the same energy, and you're going to get equal current from the two directions. So you have to tilt that. But even after you have tilted it, you will still not get current unless you have some level in between. And so that's the origin of these peaks, when you get current. So that's the Coulomb, yeah, question?
On the x-axis there, are they always evenly spaced? I mean, that's only if the levels in the quantum dot are evenly spaced,
Yeah,
right?
yeah. So there are many issues about that, and I'm not really discussing that for the following reason. No, maybe I will in the end. There is a theory paper I will bring out. But what is the issue about the level in the dots? These levels are not the single particle levels. So we will discuss that. Exactly what levels are we talking about? For the moment, let's assume they were single particle levels, just particles in a box. In that case, we know the levels go like n squared. And so these would be spaced like n squared. They are supposed to reflect the spectroscopy of the actual levels in the dot. So the issues that come in to complicate that is, firstly, the electrons are not non-interacting. We derive this n squared behavior for a non-interacting set of electrons. The electrons are interacting, and as a result, there are not only U effects, which is this E squared over C kind of effect we are talking about, but also spin effects. And so there's also something where you can not add an electron of a particular spin. And that's, you may be able to add an up electron, but not a down one. That's another issue that comes up here, and so that's called spin blocking. And I will discuss that in the next part of this nanoscience lectures when I come to spin. So that's another issue here, which we are kind of ignoring.
Quick question.
Yeah.
So how
How would they test for that? They just have a spin polarized current somehow and check whether or not they're tunneling?
Yeah. So you come in with a tip, which is spin polarized. Yeah, your tip itself is magnetic. And your that would be one way. The other way is if you look at it against theory, and theory gives you some idea about where the eigenvalues are, and they don't agree with the experiment, then it tells you that in the experiment you must have spin effects. A third way is to apply a magnetic field. And if spin is involved, it will respond to a magnetic field. And these levels will move in a magnetic field. So if it's a singlet, it won't move. If it's a triplet, it will move. Right.
Unless you get really unlucky and are tumbling through a singlet.
Yeah, you could be tunneling through a singlet. But even so, you can test that because the next voltage, if you have one singlet level, the next one cannot be a singlet, it will be a triplet. So when you change the voltage, you'll now go through this next eigenvalue and then you'll know that spin effects are involved. You see what I mean? Like, if there's a level, so this is what I mean. If you have a level here which has split into singlet and triplet, right? This is not going to split in a magnetic field. So when you're tunneling through this, you will get, so first of all, there is a shift of the energy value at which you will see tunneling. That's the first thing that will happen. So here, you would tunnel into this energy. And then now it becomes ES and ET. So if it splits, then then that voltage, gate voltage, will reflect this energy. If it had not split, it would reflect E0. If it splits, it will tunnel into ES. And then when you increase the voltage, it will now tunnel into ET. So you will see that small difference. And this difference will be proportional to the splitting, exchange splitting. So this splitting will be proportional to some J exchange, which is coming from interactions. It's just the Coulomb interactions will produce a splitting between singlet and triplet. Furthermore, if you now have a B field, so this is even at B equal to 0. And now if you have B not equal to 0, then you still have this level here, but this level will split into 3. So I took some other numbers for a slightly larger dot, which I was looking at some paper, it had a slightly larger dot of 200 nanometers, much bigger. And now the energy scales are 1 MeV there for E square over C. Okay, so this is a very, this helps me make the point about single particle levels versus many body levels. So let's look at this set of numbers, 200 nanometer dot. Okay, and I'm looking at two energy scales. EC turns out to be about 1 millielectron volt. And delta, I call it delta E. What I mean is, this is the single particle spacing of single particle levels. Okay, so what I want to discuss is, we talked about electrons in a box, right? And we had these discrete levels. And now we are talking about EC. So what is the connection between the two sets of levels? So this is just the particle in a box levels. And if you just take h bar square pi square over 2m r square, it gives you a number of 0.01. This is about 0.01. Okay. So now when you're looking at that dot, it has very closely spaced levels here. This is my delta E. And EC is a big scale. Okay, so now you look at tunneling into this and you say, well, that would suggest that when I come in with my source, my chemical potential, if I'm coincident with any of these single particle levels, I should be able to tunnel, right? That's not what is seen in the experiment. Because in the experiment, when they see this I versus you see these peaks like this, or also when you see the other one, the source drain current. Let me show you that. Sorry, that's on another plot. Yeah. So this is the current as a function of the gate voltage. These are these spikes. And again, the heights and so on are different, but the point I want to make is about the scale, E square over C. This is the current source drain current, which in the experiment looks like this. So what you see is, this is the theory. You see no current, then you see a jump when an electron passes through using one of the levels to tunnel, then again another one, and so on. These spacings here are, so this spacing here is E over C, and the current is E over RC, because RC is the time constant, RC is the time, so E over T is the time. But everywhere, whenever you look at energy scales for tunneling onto the dot, you are never picking up the delta E scale. That's what I want to bring up. That you have a dot for which the single particle states have a certain energy difference, delta E. That's not what is being picked up in these experiments. What you're picking up is another term in the Hamiltonian, which is the Coulomb interaction. And that one is dominating. So when an electron tunnels, it cares about what is the situation with all the other electrons. And it's the Coulomb repulsion between the tunneling events that is causing the current to block or come on. It's Coulomb interactions which is controlling the on and off of that little device. Okay, so this is the proof that Coulomb interactions are important on the dot because the wave functions are very confined, as opposed to the same stuff in bulk where the wave functions are very broad and extended, and then as we did the little estimate last time for this potential and kinetic energy estimates, the potential energy is not important, the kinetic energy dominates. Now we are in the other regime where the potential energy is dominating, and as a result all scales are looking like E square over C. In reality you have to look at both effects. Yeah.
So on the current versus gate voltage, we're calling the zero current region the Coulomb blockade. But that seems like it's when we're in between these states.
It's like,
delta E.
right, it's not in between delta E. So delta E is actually out of the window. So the question is, how it is in between some. So the question now becomes, how do we think about the states? Okay, so this is something which I find hasn't been discussed in any of the articles very well. So let me, and it's a very important point. So let me try to pick up on your question a little more. So there are two ways to do the problem. Suppose kinetic energy dominates. So this is kinetic energy much bigger than potential energy. And on this side, potential energy dominates. And so potential energy is much bigger than kinetic energy. The question is, how do you think about states? When you say, this is the state of my electrons, how do you think about it? In this regime, we know very well. We basically solve this problem. solve this single electron problem. It gives a bunch of states, and the many-body state is obtained by filling. Okay? It's obtained by filling all these states, and then you say, okay, here it is, this is new. And indeed, if this was the picture, you could have done tunneling, even in this situation. You can imagine, let's suppose we throw away Coulomb for some reason, and then we have these delta E things. You'll get the same phenomenology. That experiment doesn't care, what is dominating and what is not dominating. It just wants a level in resonance. So, once you have a level, you'll get current and so on. The spacing you will get will be the single particle spacing. So you'll have current on, off, and it will basically be determined by this level spacing. Is that clear? If Coulomb was not important. Now when Coulomb is important, you can't solve the problem like this. You have to work out basically your energy levels for 2 electrons is completely different from the energy level for 3 electrons. And energy level for 3 is different from 4. You have to solve each Hamiltonian separately. Okay, that's the one big difference that comes in when interactions dominate. So what you will get is, you will get something like 4 n electrons. You'll basically now, your H0 will become this. Your H0 is now E square over R. But you can't just solve one and fill up. That idea is gone. You have to evaluate H0. This is a classical problem. It's not a hard problem at some level. You can program it on a computer, where you just say, okay, I have E square over Rij, I less than j. Find me the states. So, you'll find that, typically they want to be as far apart as possible. These electrons would like to make a lattice. That would be the ground state. And then you can try to move an electron from one side to another, and that will be an excitation. And so what you will get is a bunch of states again. So you will solve this H0. You have to solve H0 for a given n electrons, Specified ahead of time. You cannot later on say, I'll be filling up so many states. And then you will get, this will be the ground state, and these are all the excited states for the n electron system. Okay, so now when we are talking about tunneling, what are we tunneling into from one to another? So what you're tunneling into is, you're looking at a dot in 2 different situations. So you're looking at sort of a dot here with n electrons, and let's say a dot here with n plus 1 electron. And this dot has its ground state and excited states. And this one has its ground state and excited states. And this energy difference between the ground states of the 2 dots is of order E square over C. Okay? But the levels have all shifted. When you went from, when I raise, so what happens is, I have my electron on the source, it hops onto this, and the energy of the dot changes, and then again it hops off, or if another one comes in, then again it has to resolve the problem of 1 extra electron. So it's a much harder concept, yes?
So I'm effectively only tunneling into the n plus 1 states. if I'm an electron looking in. So I don't see the current states, I see the states that I would tunnel into.
Yeah, yeah, because these states, so the electron is already, exactly, yeah. So when the electron is trying to tunnel in, it has to find an eigenvalue. Once it goes in, it has to be, that state has to be, it's not the right word to say it has to be an available state, yeah, but you said it better than I did. But this is what I'm trying to say, that the states of the system depend on the number of particles. So there's a picture in one of the, and somehow this I did not find discussed anywhere. Everybody makes this kind of static picture as if the levels were there and things are going on and off. But there was one review article that did talk about it a little bit. And it's a very complicated set of pictures, but anyway, I want you to look at this and this. Okay, so he did n and n minus 1. So here are some chemical potentials on the source and drain. These are the 3 filled levels. And what he's trying to show is just the ground states. So En, so he's trying to show the shift of the levels by some amount E square over C when you have one less particle, or one more particle would have moved it up by E square over C. But these pictures are a bit misleading for the reason that I mentioned, because the left, so I think my picture here, if you can just remember this part of it, that the level structure will depend on the number of electrons. And when you have n plus 1, this is clear that the ground state will be shifted by E square over C, either up or down. Relative, if it's n plus 1, it will be shifted up, n minus 1, it will be shifted down, but it's not like a rigid shift. That's what I want to say. The other levels are not rigidly shifted, and there will be some readjustment. So how do people address this? There are calculations you can do. So I want to just show you a little bit from one paper that attempts to calculate some of these things. Okay, so this paper is, so actually, before I get into this paper, let me say this. This is a calculation we could do in the class. So I will try to see if I can make up a problem on this part of it, where, because we can just throw away the kinetic energy. And then it's a classical problem of just charges. So this is a problem we can do in class with a few electrons. We can get a handle on these n particle states. So I will try to make a problem on that. Yes?
So you mentioned earlier when you were talking about calculating states about how the electrons form a lattice
Yeah.
in the quantum dot. So it seems that
okay.
it seems that the shift in energy would depend on the lattice that it was before shifting to a new one. It doesn't seem like that would
So
always be.
it's not quite a lattice. It's too small to really form a lattice.
Okay.
When I talked about the lattice, it was in the continuum with all the available space. It then formed a lattice. I'll show you what it does on here. Let's look at that picture. So this comes out of a calculation where they have done some Monte Carlo simulations. This is a dot at large kinetic energy. In this, but already some potential effects are there. So what you are seeing is if there was no interaction effect, the density of electrons in the dot would have been uniform, right? Some kind of a Gaussian. So think of it in that limit, that it's basically a Gaussian. This is already, they have put in some interaction. Now when they start turning on the interactions, not quite the classical limit. So these two pictures are in between the kinetic energy dominating and the potential energy dominating. Somewhere here is a dot with a completely uniform electronic density. Somewhere here is a dot with all the charges localized, as far away from each other. And you're absolutely right, when I add another charge, even if it's not making a lattice, it will shift all the electrons. That's the point of the many-body state. When we did the kinetic energy dominating story, adding an electron did not perturb anything else. But here, the moment I add a charge, it will shift all the other charges. And that's why the n plus 1 particle state will look nothing like the n particle state. Okay, and this is what they find in the simulation, that it does, it goes from completely uniform to what would be like, say I had a circular dot. And actually, I forgot about this, yeah, I just remembered. If you do this very simple problem, just this kind of a Hamiltonian, and you ask in 2D, how do the charges sit? So if you have 3 charges, they will form a triangle, right? You can imagine that they are as far away from each other. A fourth one, a fourth one will now make a square and so on, and ultimately, you get a ring of charges, and you can show that up to 11 or so exist on the ring, and then the 12th one goes in the center. And now you start to see some of this coming up. And then if you keep adding more and more, this is something that I remember giving it to one of my undergrads in this E&M class. They had to work out the minimum energy configurations of various numbers of particles. Let me try to dig that out. I've forgotten about it until just this moment. And then you start to get a second ring and so on. And this is a picture here which is kind of bringing in the effects of kinetic energy and showing you get sort of some kinetic delocalization within the rings and so on.
So,
yeah.
So this goes back to my earlier question. Wouldn't you expect to see a different energy shift in the states between adding the 11th particle and the 12th particle because
Yeah.
you're changing your...
You would. So this is, are you talking about this number not being identical? Yeah. And that's why there are more details in exactly the positions of these levels and so on. Yeah. So what this number is actually the number. It's not just E squared over C. It's the energy difference in the ground state of the n plus first particle system and the nth particle system. That's what. That's exactly where the peaks should be seen. And this is called electron addition energy. So I'm just giving you like more sophistication on this problem. We did the first pass, we said it was of order E squared over C, but if you look at it in detail, now what these guys do, where are the authors? So it's Harold Barringer's group from Duke. And they have done these very nice quantum Monte Carlo simulations. These are very hard calculations. And what they have done is to look at a Hamiltonian that has a kinetic energy, a potential energy, and some kind of confining potential, because it's a quantum dot, so there's some potential. They've taken a omega square. And then they calculate this addition energy. I'm not sure why they're doing n plus 1 and n minus 1 and so on. I mean, I would have just done, if it's positive bias, I would have done En plus 1 minus En. And if it's negative bias, I would have done En minus 1. So I don't know why they have done it this way, but in any case, the point is to look at the ground state difference of two dots that have n plus 1 and n. And that's the value of the voltage at which you will see these features. It will be on the order of E squared over C if the kinetic energy is dominating, if the interaction energy is dominating. Question?
I was going to say this is like a discrete Laplacian. It's a del square.
Yeah.
Not just a del. So they're averaging, adding an electron and taking away an electron.
Okay.
I think it is.
Okay. But what I didn't understand is when you apply a bias and you're looking at these current peaks, you're biasing in one direction. So you're either adding or you're subtracting. So in other words, when we were looking at those peaks, current as a function of gate voltage or as a function of source drain, either case, when we see those jumps, you're biasing it in one direction, or either an electron is hopping on or it's being pulled out. So I don't know why they took this second derivative, but maybe it was to enhance some of the features. All your peaks get enhanced and so on. Because they are looking at the energy. You see, they have the unfortunate, in the experiment you can look at current. And current is 0 or finite, it's a big difference. Energies are small, so maybe they are trying to take a derivative. But it's not totally clear. But the point of this, let me just try to emphasize the point. The point is this, that when, let's say you are looking at energy differences, if you're in the kinetic energy dominated regime, you would have picked up this difference. If you're in the potential energy, as I was saying earlier, you would pick up the ground state energy difference between an n+1 particle system and an n particle system. And that is not a trivial quantity. It is on the order of E squared over C if kinetic energy was not there at all. If kinetic energy is there, then it's more complicated to do this. And so the point they make here, let me just read out a few things here. So what they are saying here is that when there are no interactions, no Coulomb effects, the peaks are at, because of the shell effects, it's still a spherical dot, so there are some degeneracies. And that gives you peaks at n equal to 3, 6, 10, 15, etc. When Coulomb energy dominates, it changes the order to something else, to 3, 7, 11, something, something. And these are basically coming because of the Coulomb energy dominating. So even the shell structure is changing because of Coulomb interactions. Okay. Any questions? Yeah?
So in terms of the paper that we read, they kind of talk about this.
Yeah.
And he says something that I think is different than what the graph shows.
Mm-hmm.
So they've got the current versus the gate voltage, and this extra energy, delta E, is needed to add a third electron, which I think is correct. But above, he says the spacings between the peaks are not constant, and significantly more energy is needed to add the second, 6th, and 12th electrons. So I guess I'm confused about how the levels move through the chemical potential of the source, and how they're getting the spacings that they
Right.
are.
So what he is referring to is he's not talking about this picture. He's talking about this picture, but basically he's not talking about this delta E story at all, because delta E is tiny. So this 2, 6, etc. is coming from the fact that even here, these are n particles. So we should really only be talking about n particle states. And even in these n particle states, there are degeneracies. Okay? So what we are, and those, when they talk about shell effects, they are shell effects. So in this situation, the shell effects would come as follows. En would be h bar squared pi squared over 2m L square or whatever times some n squared plus m squared plus p squared. Okay, this is what we mean by shell effect, that you can pick different combinations of n and p and you get the same energy. And that is, the energy does not change for, say, a certain number. So when you say, let's say here they claim, so when they are non-interacting, it's like, say, 3 something something, 3, 6, 10, 15. So we should be able to get those numbers just by filling up the non-interacting case. Okay? Now when they talk about shell effects for the interacting problem, you now have to talk about degeneracies of these multi-particle states. And I don't know those numbers offhand, but those are definitely different. That's what he's pointing out. And this would depend on more details, whether it's a lateral dot or a vertical dot. The precise kind of dot will also change that. So in that article, it's something else, 2, 6, some other set of numbers. So that's not cast in stone. But the fact that there will be magic numbers is just coming from degeneracies of some set of levels, many body levels in the case that that article discusses, though they don't clarify that. Okay, but if you continue to ask me if you still have questions about it, because this is an issue totally glossed over, and I want to clarify this through a problem set if I can make a nice one. But it is something, and the reason I'm alerting you is without this aspect, you cannot understand the energy scales at all. Because then you will wonder, you will wonder why is it that if I have a 200 nanometer dot, why am I not tunneling through these other intermediate levels? Why do I have to go to 1 millivolt to tunnel? I have 100 levels in between. Why am I not tunneling through that? It is not a question of sensitivity. And the answer to that is having to rethink the states.
Quick question.
Yeah.
You may have said this, I don't know, but what is that omega term?
Oh, so when we said here we had a particle in a box, I just sort of solved my Schrodinger equation with infinite potential at the edges. So this one, they've taken a harmonic potential, which is a way of depicting the confining potential for that particle. And the reason they've taken something like this is because of the way they put gates to confine it. It's not a hard wall that confines the dot. Let me just show you that picture of the SEM we talked about perhaps here. So you see the dot is made by putting these gates, which sort of confines it in some soft potential. So they just do that omega squared. Okay. So we got the Coulomb, so this was the Coulomb oscillation, these are the blockade regions, and then this is the, these steps when current comes on and so on is called the Coulomb staircase. Okay, and this is an important aspect of why it is called a transistor. So I'll try to review, maybe it's a good time to just review briefly what we would have gotten for a classical FET, not this quantum FET. So for a classical FET, and I just kind of put my notes on this from last quarter, so which we didn't actually get to discuss in the class, but let me just bring it up here. So let's see. The typical FET story is something like this. You have and I think many of you are working with such geometries. This picture got tilted. Okay. I don't know why.
You can usually rotate. If you go to view, rotate view, the fourth one down.
Very good. So it's again the same thing. We have a source, a drain. Okay, so essentially what is done here as a source is just a heavily doped region, N-type region, let's say, heavily doped. So it becomes conducting. Here's the drain, and in between is the channel. So this is the analog of our dot. Okay? And the gate are these plates on top, which is being used to control the channel. Just like here, the gate was being used to control the levels on the dot, here the gate is being used to control the channel. And now there's something interesting happening with the depletion regions. So let's look at that. The whole thing is rotated.
View.
Here.
No, it's good, it's
Oh,
good.
it's good. Okay, good. I thought I did it twice for the other one.
You did it 3 times.
So then, okay, good.
You should make it bigger.
I'll make it. Okay, that's good. the way it becomes a transistor is basically that a transistor is a three-terminal device. So what we are going to see is something like this. Let me just show you one of the characteristics. Yeah. So what we are going to see is, I'll show you how this comes about in a bit, but basically this is the kind of characteristic that you have through such a channel. I versus VD, this is the drain voltage, source drain voltage. It increases and then flattens out. Okay, why this happens is because of the particular depletion region antics in that device, and I'll show you why it happens. But this is very similar to what we were seeing in the dot. Source drain, it was 0, then it turned on, then it went up, then it went up. So this is kind of a transistor is nothing but a device which has two aspects. One is it has a current voltage, a characteristic which is not linear. It's non-linear. And the second part is that it can be controlled by putting a gate. So by putting a gate, you can basically move that up and down. Now, our dot is able to achieve more than that because it does not have just one off region. It then comes in, when the second level comes into the picture, you then have another step and then another step. So it is a multiple set of these steps, and then those steps can further be controlled by a gate. So it is a more versatile device, considerably tinier than this, but more versatile, where you get the IV on and off happening multiple times and controlled by a gate. Okay, now let's try to see how the origin of this effect is completely different in the two. There's no connection between why it turns on and off. There it is happening because of quantum tunneling and levels coming in and out of resonance. Here it's happening because of the way one is manipulating the depletion region. So the origin is totally different. Okay. So the point about that is, here's what I put down. So you start out with a PN and a channel in between, and the width. So the width of this depletion region. Here's the depletion region. The width of the depletion region, as you remember, is controlled by the amount of doping, right? So if I have no bias on this, it's just the amount of doping that controls that depletion region. So here it is. Okay. So essentially the depletion is controlled by, where is that crucial expression? Sorry, I don't have that. No, I don't have that. But if the doping is high, the depletion is smaller, and you have that charge conservation relation. Do you remember that? Okay. And then the next step is you can change the depletion region by biasing it. So if you put a forward bias across the junction, it reduces the depletion width. If you put a negative bias, it increases the depletion width. And this is what you're going to play with in that, in changing its characteristics. Okay, so now the next step. So step 0, you start out with some basic depletion region. Now you apply a bias across this. Okay, so this is a gate. Sorry, this is the drain. Sorry, I'm getting confused. Yeah. So this is the drain voltage from here to here, which means at any point, this is 0, this is VD, at any point there's a potential which is varying. Okay? And basically if I'm reverse biasing the PN junction, then the depletion region is not constant as you go from source to drain. Because every point sees a slightly different potential. So as a result, the width changes. So here the width is small, I'm reverse biasing it. As I go toward the drain, the width gets bigger. And so this is the picture. sorry, the width is getting bigger. Okay, and that means all the charge which is trying to flow through this channel, this N channel, is the width is kind of squeezing off that region. So at some point, the depletion width gets so big that it pinches off. This is called pinch off. The channel width is pinched off. And at that point, the current levels off. Because now the current is only due to whatever the minority carriers are. Up to now, the current was due to the majority carriers. And it was changing. But once it gets pinched off, so here, this is another thing which you can read many books and they don't tell you why is the current constant? Why doesn't it now just go to 0? It bothered me for a long time. I had no idea why the current was not just becoming 0, it's pinched off. And at some moment, one of those shower moments, it sort of occurred to me that it was now the minority carriers that are still going to go through and give you this little current. So you can think about all these things.
Why are they even increasing as the channel gets narrower?
Oh, it's not increasing, it's relative, so there's a drive which is pushing the current. So whatever, there are lots of electrons available. So if relative to this, the slope is decreasing.
Okay.
The slope is decreasing. So the current is decreasing for the same amount of drive that you are putting. But at this point, at the pinch off, then it becomes a constant. And the gate voltage shifts that. So the point is beyond, so here in this linear regime, the current is controlled by the drain. How much bias have you put? That is controlling the current. Once it pinches off, the current is controlled by the gate. Okay, so that's why it is called a 3-terminal device, because you have the 2 terminals, source and drain, and the gate. They are all controlling. And that is when you start to get amplification, because in a way, the resistance of the junction is basically V over I and delta V over I, and here it becomes basically constant. So you get a very large amplification. Okay. So the key point is that it's being used as a switch. That is that's one of the applications of the transistor. It's a switch which goes on and off. And in this, that is the reason people call the quantum dot in this geometry also a single electron transistor, because it can control the on and off of charge. But as I said, while the source, drain, gate, this language is very similar, the origin of the effect is quite different. But in principle it's the same. So now that is what people refer to when they say single electron transistor. And let me show you that. So I think I tucked it in somewhere. So the idea of the single electron transistor was first proposed by these two theorists, Averroes and Likarev, and then first fabricated by Fulton and Dolan, and that's what it looked like. I couldn't even believe this was a single electron transistor. Where was the single dot, or where was the quantum dot? But so they after reading through all that, because they're talking about 0.03 micron wide. But nevertheless, this is what happens. The idea comes, the first thing doesn't quite look like that, and so on. But it's at these little junctions that they are hoping to get a few particles touching and so on. So it's not a very clear nanodot at all. But that was the first realization of that object. this is a more recent paper. The title is A Single Electron Transistor Made from a Cadmium Selenide Nanocrystal. And so what they have is all of these are like nanocrystals of cadmium selenide. Cadmium selenide itself is a very interesting material, and there will be another homework on its optical properties. But anyway, here what they do is they throw around these, so here it is. So somewhere, so we have that idealized picture that I drew. This is the reality. So the dots are always there somewhere. And they just hope that there is one of the little particles will be helping them make contact. So it's still not like just one dot. But in any case, the experiments we talked about in that review article, the Physics Today one, those are all single electron transistor configurations where one dot was placed between these tunnel junctions. This is yet another realization. And they are using also some unpronounceable linker molecules to try to connect gold leads and so on. I didn't get into all the details. The point is, so these are 5 nanometer crystals. And this is what they are trying to show. This is a nice figure because it shows I versus V. This is the source drain voltage. And you see this nice flattening. So there's no current when V is 0, and then the current starts out. And here is the gate voltage position. So this is the conductance as a function of gate voltage. And this is one of the peaks that I was showing. And at this point here, the current is very small because it's in some position like this. Here you're at the peak of the gate voltage, and then the source drain current versus V has a more linear behavior. So it's that. Question? Questions about this?
What
Yeah.
temperature do they measure that at? Because that looks,
What temperature?
yeah, because that looks really broad. Like
Yeah.
two
They
volts.
measure it at about 5 Kelvin. It's a 5 nanometer dot. So the levels are quite far apart. I mean, the E square over C is quite a large scale. We worked it out. So I think, what did we work out? 500 would be the temperature, equivalent of E square over C. Yeah.
So I'm not sure I understand the distinction between the two operating voltages
Yeah.
and gate voltages, or why we expect flattening or the linearity.
So let's make our picture here. So here is a level. When you're at the lower point, basically you're trying to, right. So you're basically applying always like this. So this is mu1, mu2. And let me just, I'll always fix these.
Well, that's what's being swept in the inset.
Yeah, that's
right?
being swept in the inset.
Right.
So let's say I have first fixed it here, and then I have a very, and I'm tuning my VG, I have a very small current. So that would mean that there is no level that is in place, right? So,
So then your first available level is above mu1, right?
is above.
Is above mu1.
Okay, I was going to
Well-
move. I was going to move mu2. Okay, it depends.
But the gate controls the dot levels, right?
The
So
gate controls the dot level.
at a
So first,
large negative gate bias,
yeah.
your
level is
dot
Okay,
levels are
my
still
top
up.
level is here.
And then as you're sweeping the bias voltage, then you're moving mu1 and mu2 up and down.
Yeah, you're going to fix one of them, and then you're going to start to move the other, right? But in order to get tunneling, this level has to be able to fall into that. So very negative. So don't worry about the value of VG, because it has some arbitrary offset. So let me start here and see if we can explain that. This is the dot level, let's say. I'm always going to set this to be 0. I won't move that. I will move mu2 relative. So here's the dot level. No current, so I'm in that VG small condition. Now I start to sweep the the voltage on the inside, which is my mu2. So let's say I make mu2 negative or positive, whatever, in one direction. So when mu2 comes here, right? Now that is the first time an electron, there are lots of electrons on this source. It will hop here and then it will hop here, right? That's the first time. Now as it keeps going down, I can still keep hopping off. I can still hop and I can still hop off there. So as I move mu2, so for a while there was no current, and then the current starts and I keep getting current. And the other thing on the other side. And then on the top, I'm already in a position where the level was, the gate voltage had been tuned to have this level in this situation. So this is case 1, and in the second one at the peak, we have already, this is mu1 at 0. The dot was already there, and this is mu2. So this was already hopping. I already had current flowing from there. You didn't have a question? No.
How do you know you have the levels to cells in one? The dot stays, or the node stays there instead of
Here?
yeah.
How do I know? Oh, no. I'm saying when I have, so I'm using this logic, when the gate value is such that I have a large conductance, this must mean that the level was, that the dot level, so here is the gate voltage. The gate is moving these levels up and down. So the gate has moved it such that at minus whatever volts it is now in line with, at the same energy with the source. And then it can hop. Okay. Okay, so that's basically the story, and then they get this. So they get this nice diamond when they now plot. So the diamond is just a plot of the. If you take a derivative of the current versus voltage, di dv, it has peaks. Even for both cases, for the gate voltage variation, also you have peaks, and when you have the source drain voltage, you have these steps. So when you take a derivative, you get a peak at every step. And then they map out the intensity of the conductance as a function of, in this plane, V versus Vg, and they get these diamonds. And that's another defining feature, which basically says, wherever you have these white diamonds, which are blue diamonds in that paper, you have no current, then you get current here, and so on. And then they try to analyze it and so on. But every place, they have glossed over what exactly these states are. And for the most part, you can go through your arguments without worrying about too much about these states. And you can just bravely make your, something hopping off. It's when you want to understand what is the level spacing, what is the height, then you have to start worrying about degeneracies and the details. That's when you have to really think about many particle states and their degeneracies. And at that point, you have to sit down and either you can work in the classical limit and get quite far. And I've also showed you that if you want to get serious and really do the calculations, then you have to do some kind of quantum Monte Carlo. So that kind of gives you a big picture. Now what you could do is take a look at some of the stuff I've put on the lectures, and it has all of this. Not all the discussion, because the discussion is kind of determined by your questions, but a lot of the figures are there. Okay. So see you tomorrow. I will give, tomorrow I'll talk about metallic dots. and we will talk about surface plasmons and yeah, some of these things about the dielectric function and so on as a function of omega. Oh yeah.